everyone, and welcome to this explainer. I am absolutely thrilled you're here today because we are embarking on a pretty fascinating mathematical journey through physical chemistry. We're going to demystify a phenomenon you actually interact with all the time. Think about when road crews scatter salt on icy winter streets to melt the ice, or why ocean water doesn't freeze at the exact same temperature as a freshwater lake. But we aren't just going to skim the surface here. We're looking at it through the strict, incredibly elegant lens of thermodynamics. We'll break down exactly how and why a liquid's freezing point drops when you add a solute to it, tracking the math from a basic physical definition all the way to the final thermodynamic equation. So grab your notebooks because this structural derivation is logically brilliant. Okay, so here is our roadmap for today. First, defining the freezing point. Second, visualizing vapor pressure drops. Third, deriving with Raoult's law. Fourth, unpacking the cryoscopic constant. And fifth, arriving at the thermodynamic final equation. Let's get right into it. Let's dive right into this with Section 1, defining the freezing point, and really understanding our baseline state. Now, you might be wondering, before we can even talk about a freezing point changing, what actually is a freezing point in the strict language of physical chemistry? Well, the freezing point is the temperature at which the vapor pressure of the solid and the liquid are exactly the same, meaning they are in perfect equilibrium. It's not just about, a liquid getting cold, it is about hitting this very specific active balance point. Think of it like a really busy store. The exact number of molecules freezing into a solid perfectly matches the exact number melting back into a liquid. This equilibrium concept, it is absolutely the foundation for everything we are about to calculate. Moving right along to Section 2, visualizing vapor pressure drops. Graphing the phenomenon. Let's actually visualize what happens to that delicate balance when we introduce a solute. Check out the top curve on this graph, labeled solvent. That represents our pure liquid. Right below it, we have solution 1 and solution 2. When we add a non-volatile solute, the overall vapor pressure of the solution actually drops. And because that vapor pressure is lowered, the solution has to reach a much lower temperature before its vapor pressure can match the pure solid solvent and actually freeze. You can literally see those intersection points, marked A, B, and C, shifting over to the left toward lower temperatures as the concentration of the solution goes up. To put some math to this shift, let's look at the horizontal temperature axis. We define T0 as the freezing point of the pure solvent. Then we look at the new lowered freezing point of the solution, which we'll call Ts. Mathematically, this depression shift is basically just a simple subtraction. Our pure freezing point minus our new solution freezing point gives us delta Tf. But wait, how do we actually link this temperature drop back to the pressure drop we saw on the vertical axis? Well, we use a little geometry. If we look closely at that graph and assume these curves over these tiny intervals are practically straight lines, we can form triangles. By comparing similar triangles, specifically triangle ABD and triangle ACE from the graph, we get proportional ratios. AD over AE equals BD over CE. When we plug our pressure and temperature variables into those geometric ratios, boom, we arrive at a brilliant, simple conclusion. The drop in vapor pressure, delta P, is directly proportional to the depression in freezing point, delta Tf. Which brings us to Section 3, deriving with Raoult's law, connecting temperature to moles. Okay, since we know temperature depression is directly tied to vapor pressure drop, we can take a massive leap to connect these physical changes to the actual chemical makeup of our solution. But before we do the algebra, let's establish our players. We've got our temperature drop, plus the physical weights and molecular masses of both our solvent and our solute. Now, Raoult's law for very dilute solutions tells us that the change in vapor pressure is proportional to the ratio of moles of solute to moles of solvent. That's N2 over N1. And since we just proved that our temperature drop is proportional to our pressure drop, that means delta Tf is also proportional to that exact same mole ratio. Let's expand that mole ratio out a bit. Moles are just weight divided by molecular mass, right? So the ratio becomes W2 times M1 all divided by M2 times W1. Now, here is a seriously clever trick. The molecular mass of our pure solvent, M1, is a constant value. It never changes for that specific solvent. So we can just sweep it up into a brand new general proportionality constant, which we'll call K. This gives us our substituted equation. The temperature depression, delta Tf, equals our constant K multiplied by the weight of the solute divided by the molecular mass of the solute times the weight of the solvent. Next up is Section 4, the cryoscopic constant explained, where we introduce Kf. That last equation is a great start.
But honestly, that constant K is a bit too arbitrary for practical everyday lab work. To standardize things, we introduce a magic number to our equation, 1,000. By mathematically multiplying and dividing our previous equation by 1,000, we don't change its fundamental value at all, but we completely transform its utility. It allows us to relate our calculation to exactly 1,000 grams, or 1 kilogram, of solvent. By rolling that 1,000 into our constant, we transform our generic K into the cryoscopic constant, or Kf. It is strictly defined as the temperature drop produced when exactly 1 mole of solute dissolves in exactly 1,000 grams of solvent. We've taken a relative proportional shift and anchored it to standard, universally measurable units. So, the absolutely crucial point here is how elegant the math becomes once we make this substitution. Because the part of the formula that reads W2 times 1,000 divided by M2 times W1, well, that is literally the chemical definition of molality. So our massive multivariable derivation completely collapses into this beautifully simple final formula. Delta TF equals KF multiplied by molality. If you know the constant for your solvent and the molality of your solution, you instantly find the freezing point depression. It's a real game changer. All right, final stretch, section 5, the thermodynamic final equation, calculating KF via Van 't Hoff. So we have our standard constant, KF. But what if we need to calculate KF itself entirely from scratch? To do that, thermodynamically, we rely on the Van 't Hoff equation. The key variables here are T0, which is the freezing point of the pure solvent in Kelvin. We also need LF, which is the latent heat of fusion per gram of the solvent. You can think of this as the exact amount of thermal elbow grease required to break apart 1 gram of the frozen solid. And finally, we need R, the universal gas constant. And this brilliantly illustrates how they all combine. The cryoscopic constant, Kf, equals the gas constant multiplied by the square of the pure solvent's freezing point, all divided by 1,000 times the latent heat of fusion per gram. It is genuinely incredible to see how an everyday property, like how easily your driveway freezes in the winter, is actually dictated by these deep-level, fundamental thermodynamic constants. Just as a quick tip, I do want to point out an alternative form of this equation that you might encounter out in the wild. Sometimes, instead of looking at the latent heat of fusion per gram, you'll be given the latent heat of fusion per mole, represented by delta HF. Actually, if you use the per mole value, you simply bring the molecular mass of the solvent, M1, up into the numerator. Both forms are perfectly valid thermodynamically. It literally just depends on which units of latent heat you're working with. Well, we have built quite an incredible logical tower today. To wrap up, your 3 main takeaways are: 1. Freezing points drop because vapor pressure drops. 2. We can link this pressure drop to the exact amount of solute using Raoult's law and the cryoscopic constant. And 3. This entire relationship is governed by strict thermodynamic constants. But all of this math relied heavily on one specific condition from our very first step, that the solute we added was strictly non-volatile. So I want to leave you with this provocative thought to explore next. What happens to the equations?